Born-Oppenheimer approximation or the adiabatic approximation. Solid-state physics or electronic structure calculation, we call it the Born-Oppenheimer approximation, but more generally, this is also known as the adiabatic approximation. Or the adiabatic method. It's a way to separate the fast motion, the equation of motion for the fast particle with respect to the slow one. So the Born-Oppenheimer approximation is what we will use to determine the property of the structure, the atomic structure, starting from the electronic structure. Of course, in a crystal, the position of the nuclei, the distance between the nuclei will depend on the bonds, which are due to the electrons, to the valence electrons. So clearly, also the structural properties should depend on the electronic structure. However, so far we have forgotten in the course about the nuclei as particle, as quantum particle, about their dynamics, about their equilibrium position, how it depends on the electronic structure. So now we would like to address that. And also, we have assumed so far that the Schrodinger equation for the electron just depends parametrically on the position of the ions. However, in principle, in general, the equation of motion of the electron and ions are coupled. And actually, it's the adiabatic approximation or the Born-Oppenheimer approximation that allows one to separate the equation of motion for the electron, the Schrodinger equation for the electron, from the part related to the ion, from their motion. So it's a coupled system in general, and this is a way to separate and treat first the electronic part, and from that solution to get the structural properties. So now we are going to go back to the original Hamiltonian for the two types of particle, electron and nuclei, and we are going to discuss how to separate it, and this will be done with the Born-Oppenheimer approximation. So with this approximation, we will have access to the properties of the structural properties of the crystal, the equilibrium position, the equation of motion of the nuclei, starting from the solution for the electron, from what we have obtained for the electrons. So let's go back now to the original Hamiltonian. So this is the full Hamiltonian for the electron and the nuclei. So in general, it includes a kinetic part for the electrons. So for the kinetic part, I use the T. Then there is an electron-electron interaction and an electron-nuclei interaction. So these are the first three terms. And then one has also a kinetic part for the nuclei and a nuclei interaction also. So this is in general the full Hamiltonian with this T corresponding to the kinetic part. Okay. Now, the explicit form is for the kinetic part, we will sum over the electron, their momentum, Pi, over 2 times the mass of the electron, plus the electron-electron interactions, so it's a double sum. I write it as sum over I and I prime, but I and I prime, I different from I prime. So E square over the difference of I prime minus of I. So this is for the electron-electron interaction. Then, which is repulsive, then one has an attractive electron-nuclei interaction. Minus sum over I and capital I. I will use for the ion capital for the nuclei capital letters and for the electron small letters. So E square Z, the atomic number of I minus capital I. So this is the electron nuclei interaction, and then a sum over the nuclei of their momentum, Pi capital over 2 times the mass of the nuclei. So this is for the kinetic part, and plus the nuclei interaction, 1/2 the sum, the double sum with I different from I prime, E square Zi times Zi prime over Ri minus Ri prime. Okay, so this is in general the full Hamiltonian with the momentum Pi for the electron, which is the quantum mechanical operator, the gradient with respect to the position I. And for the ion, the nuclei, similarly, P, capital P is H bar over I, the gradient with respect to the nucleus position. Okay? So, in what follows, I will, to simplify the writing, I will use a vector R for the electronic position, which is just a combination, a vector that contains the position of all the electrons, that is R1 to Rn, with small n the number of electrons, so just a long vector with all the vectors of the position of the electron, and similarly for the nuclei with R capital N. So, given this Hamiltonian, the Schrodinger equation will be this h times the wave function with the position here of the electron and of the nuclei as variable, and then this is equal to E C of R capital R. So in general, this is the starting equation for the overall system, electron and nuclei as particles, quantum mechanical. So in what follows, I will simplify and just focus on an electron and a nucleus, but the derivation can be done more generally along the same lines for more electrons and nuclei. So for simplicity, I will just formulate and derive things for one electron and for one nucleus. So in this case, the Hamiltonian is just minus h bar square over 2m, where m is the mass of the nucleus, gradient square with respect to the position of the nucleus, minus the kinetic part, well, plus the kinetic part for the electron, which comes square over 2m, where this m is the mass of the electron. And then one has the electron-nucleus interaction, Z squared over R minus capital R. So this is the simplification in the case of one electron and one nucleus, the full Hamiltonian. And here you can recognize the part that we have used so far, that is the Hamiltonian for the electron. That depends parametrically on the position of the ion. Okay? So this is the part on which we have focused so far, considering that the position of the nucleus is just a parameter. Now, there is something important one should note already at this point, is that there is a huge difference between the two masses that appear, the electron and the nucleus masses. And the mass, that is the capital M over small m, is of the order of 1,000 to 10,000. So huge difference in the mass, and this is the reason we will be able to use this Born-Oppenheimer approximation. Okay, so this is the Hamiltonian. And as I mentioned so far, we have focused just on the electronic part, that is, we were solving this equation, each for the electron, phi n of r, depending parametrically on the position of the nucleus, is equal to n. It also depends on r, phi of small r, capital R, n of O. So there, so this is the Schrodinger equation we have been solving so far, considering that the R was a parameter, the position of the nucleus. We were fixing the position of the nucleus and solving this for the electron, where phi n is the solution that depends on the position on the electron. Okay? So now we want the full phi, psi, sorry. The psi, and of course the total energy, the corresponding energy E. So what one can note is that for a given position of the nucleus, one can always write the full psi of R. So for a given position of the nucleus, one can always write the full psi that depends for that given position as a sum over all the electronic eigenstates with a coefficient here Cn of R of this phi n of R at that given R. That is, the solution of this Schrodinger equation is a complete basis at a given R to write any full wave function psi of that R. So this is a complete basis. Or a complete basis set at a given R that gives us any wave function psi. So in general, one can write the psi in this way without any loss. And by continuity, this can be done at different R. Okay? This is a complete basis because these are the solution of this Schrodinger equation. So the wave function psi of small r can always be written this way at a given r. And then by continuity, one can do it also for other capital R. So now with the wave function written this way, I can apply my full Hamiltonian, which was h bar square over 2 capital M gradient square with respect to the position of the nucleus, minus h bar square over 2m, the mass of the electron, gradient square with respect to the position of the electron, and then the electron-nucleus interaction, which I will just write as V of R minus capital R. It's the Coulomb interaction, but I can write it more generally as the potential V of R minus capital R. So this I applied in the wave function written this way. So sum over n of the coefficient Cn of R phi n of small r capital R. So this is my Hamiltonian H on my wave function, acting on my wave function C. And I have therefore to apply this second 2 times the derivative on this wave function, the product of the wave function that depends on both on R here. So if I apply this on this, I will get minus h bar square over 2 capital M, and then this will give me sum over n. So I apply first this on the first wave function twice. So gradient square with respect to R of Cn of R. I will also put a parenthesis here over my sum. So I'm applying the second derivative on the product of these two of this wave function. So this gives me the double derivative on Cn times Cn and then I get 2 times the derivative of the first wave function times the derivative of the second wave function, so 2 times gradient with respect to capital R of Cn of R times the gradient with respect to the nucleus position on the second wave function here. So 2 times derivative of Xi times derivative of Psi plus the second derivative on the second wave function here. So Cn of R times the gradient square with respect to R of phi n of R capital R. So this closes the parenthesis. And that on the sum, and also that on the mass here. So this is for this term acting on this, okay? Then I have, the second operator derivative with respect to the electronic position, but it's only acting on the second wave function here. So there I'm getting sum over n of, I can take this in front, so Cn of R, and then I have my operator that acts on the second wave function, h bar square over 2m gradient square with respect to the electronic position plus v of r minus capital R that act on Cn of R capital R. So, yeah. So this is for this term acting on this. And then this is equal to the energy E times the wave function sum over n Cn of R times Vn of R capital R. Okay? Now there is something one can recognize here. This is just the Hamiltonian for the electron, H E of R. Okay? That is acting on the eigensolution of that Hamiltonian. So this part will just be give the eigensolution. So now I'm a bit straight here. So this part here will just give En of R times Cn of R capital R. Okay? All right. So now what I'm going to do is just use this equation here equal to this, and I will just integrate over R cube an eigenstate Vm of the electronic part of the electronic problem, that is a solution of this HE here. So Vm star of R capital R, I will integrate this times my HC equal to EC. So what I will do is take this part of the equation that I have written here is equal to ED. I will multiply by Cm star and integrate. Okay? Because I will use the orthogonality relationship between the Cm and Cn that are solution of this Hamiltonian. So this will simplify things. So I project on the left on one eigenstate of the electronic problem, phi m star, and I integrate. And what I will obtain from that, okay, I will write it there. I will keep this. So, what I will obtain doing that is here I'm going to get minus h bar square over 2 capital M, the gradient square with respect to the nucleus position, Cm of R. Because if I'm multiplying by the complex conjugate here and I integrate, I will obtain something non-zero only when n is equal to m because of the orthogonality condition. So I just remain with the gradient with respect to the nucleus position of Cm, and then the other part. Here, the integration gives me 1. The next term, this one, will give me minus h bar square over m. I simplify the 2 from the numerator denominator. So then I have sum over n, a gradient with respect to the nucleus position Cn of R. That multiplies my phi m gradient with respect to R. N. So there I remain with this term. And then, so this comes from here. Now I have this term, which will give me minus h bar square over 2m, sum over n, Cn of R phi m gradient square with respect to R n. So this is the third term. And then the last one will simplify. I will have just Em of R, Cm of R, again using the orthogonality condition. And this will be equal to E Cm of R. Also, on the other side, it simplifies because of the orthogonality relationship between the eigenstate of my electronic Hamiltonian. Okay? You agree? All right, so this is what we get. And we have now something that is close to the end result. So there are two terms which involve the derivative with respect to the what I will call the slow variable, the position of the ion on the electronic states, either as simple derivative or as double derivative. And these terms here, this one and this one, I will call them or they are called the non-adiabatic terms. And I will assume that they are close to zero, very small. So this is what we will assume, and I will show you later on that this is this makes sense. That these terms are actually very small. There are reasons for that. One derives, well, I will show you later on why. But for the moment, assume these terms, which are the non-adiabatic terms, are close to zero. And in that case, the equation simplifies drastically. What one gets is minus h bar squared over 2m, the gradient with respect to the nucleus position, plus En of R, also, sorry. Cn of R is equal to E Cn of R. So, with this term vanishing in blue, so these two terms in blue vanishing, one gets this equation, which is just an equation with a Hamiltonian here and the wave function for the nuclei. So one gets a Schrodinger equation for the wave function of the nucleus, where the potential is actually the eigensolution of the electronic problems. Okay? So we have an equation from which we will get the solution for the nuclei, for the eigensolution for the nuclei, where the potential is actually obtained from the solution of the electronic problem, which is the eigenvalue of the electronic problem. That depends parametrically on the position, but now it's essentially it gives us our potential. Okay, so now we have obtained this way a Hamiltonian equation. Hamiltonian equation for the nucleus, or nuclei in general, can be generalized. And where the potential is given by the eigenenergies. The eigenenergy of the electronic problem. I will show you in a moment, I mean a little bit later, why these terms are small. But essentially, they involve the derivative with respect to the parameter or the position of the nuclei on the electronic wave function that basically depends very, very smoothly on the position of the nuclei, in the sense that the electron being much faster when the position of the nucleus moves, basically they move with it, and the derivative, as you will see, will give something that is small when one divides by the mass of the nucleus compared to other terms like this term in the Hamiltonian. Anyway, I will show you this a bit later, but now I want you also to see that this equation, in this equation, the E here will depend on the state in which the electron is, in the case of that is on the quantum number n of the electron. So this E will depend on the quantum number n that is related to the electrons. So for each n, and in particular for the Born state of the electronic problem, let's say n equal to 0, one can solve this, and one has eigen values that can be labeled for the nucleus in eigenstate that I will call lambda equal 1, lambda equal 2. So we have two quantum numbers related to the electronic part and to the nucleus part. That is, the nucleus solution will depend on, the E will depend on first which n one chooses for the electron, and then one has all the eigenstate of, for a given n for the electrons, all the eigenstates related to the vibration of the nucleus that we will label with the lambda. Okay? Well, mathematically, they are, that's what comes out. So now let's see in practice with an example how it looks like. And let's consider the case of a diatomic molecule. So like, for instance, H2 minus. So the example I will consider is a diatomic molecule. For instance, H2 plus, that is the 2 proton with an electron. So in the case of diatomic molecule, if I plot the energy as a function of the interatomic position R, so R is the interatomic position. In this case, the distance between the 2 protons. Now, if I plot first the eigenenergies En for the electronic part, En of R, I will have a ground state, E0, and it will look if for each position R of the nucleus I plot, or I put the points for the energy of the electronic problem, I will get a curve that is actually going to look like this, becoming repulsive when the proton become very close to each other. So this is the n equal to 0 of R. So the solution of the electronic problem as a function of the position between the nuclei. So I have 2 nuclei, and as a function of their distance, I solve the electronic problem, and I plot here the eigenvalue. Okay? So this is the ground state, which becomes a curve because it depends parametrically on the position of the ion. So this would be the n equal to 0 value. Then I have other, in my electronic spectrum, for each R, I will have a state higher in energy for n equal 1, so I can plot it this way. So this will be the state that I would obtain for n equal 1. And so on. I will have some other state, n equal 2, and n equal 3, and so on. These are the eigen state of the electronic problem at the given position of the 2 nuclei. What we have solved, when solving the Schrodinger equation for the electronic problem. However, now, once I have for a given n, so in particular for the ground state, this curve becomes the potential of an equation I have to solve and to get the wave function of the nuclei, which gives me this E, which will become the the energy of the full system. So we have seen that this energy now depends on lambda. So for this potential, if I solve the equation that I just showed you for the nuclei, I will get levels, n equal lambda equal 0, which would be the ground state. And let me plot this a bit better. Lambda equal to 0, lambda equal to 1, lambda equal to 2, and so on. I will get a series of levels with this potential, solving my second equation. Okay, and these are going to be the E of n equal to 0 for the electronic problem, and then my lambda will gives me the other eigenvalue with lambda equal 0, 1, 2, and so on.
Excuse me.
Yes.
Well, solving the hydrogen atom problem, which is like almost similar to this in some sense, we didn't introduce the parameter R.
Well, yes, because we assume it's at the origin.
So, in that case, we just had like n equals to 1, 2, 3, 4, and different energies. Here we also introduced parameter R, and for each n, there is this dip at the minimum energy at a particular value of R.
Yes.
Does this dip for different n, it's same for, like is that same R or is that different R? It
can be different.
Okay.
This would correspond to the equilibrium, which is the relevant state in our problem. What I will tell you next is actually in the Born-Oppenheimer approximation, one will focus on the n equal to 0, the ground state of the electronic system. And the reason is that the motion of the electron is so fast that they will immediately go to the ground state. So they adjust immediately to the displacement of the ion, and they are in their ground state. And if one is at room temperature or temperature of that order, basically it's enough to focus. One can just focus on the electronic ground state, that is the curve for n equal to 0, small n equal to 0. So this part will not need to be considered. But to be complete, I'm first giving you everything and then telling you what one can neglect. So for n equal to 0, in principle, solving the solution, the equation, the second equation I gave you, the latest equation I gave you, one has a series of levels here which correspond to the nuclei vibration in this potential. But the same can be done then from n equal 1, one will obtain a series of levels here, and further also for the next potential. So in principle, this is what one will get for the full problem to get this energy for the overall Hamiltonian nuclei plus electron. Now, let's come to the simplification. So, and this comes from the mass. Because the mass ratio of the nuclei on the electronic mass is so huge that is of the order of 1,000 to 10,000. Then the spacing between the vibrational state here is going to be extremely small compared to the difference between the electronic eigenvalue. So this is the statement, and then I will tell you why. I mean, mathematically. So the spacing of the vibrational mode of the nuclei is much smaller than for the electronic levels. And the reason comes from the mass, and something you have already seen in quantum mechanics, that is just the harmonic oscillator. If you consider this curve close to the equilibrium, it's like a parabola. It goes quadratically. So if I consider here that my potential where in the region that is relevant, that is near the minimum, is a parabola, then I know how to solve the equation that is for, so this is to show you this, that is for harmonic oscillator. The Hamiltonian is of the type minus h bar square over 2 times the mass. The second derivative, this I'm just going in one dimension. I have just one variable here, the position, interatomic position. So the second derivative plus my quadratic potential. So this is the Hamiltonian. If I consider that x is just the displacement with respect to the minimum, this is the Hamiltonian I would have to solve for the nucleus vibration, considering that my potential is essentially parabolic in the region near the minimum, which is the relevant one to get the lowest state. So the harmonic oscillator, you should know that the level spacing that h bar omega, the energy, is given by square root of k over m. Okay, this is the solution for the harmonic oscillator. In one dimension, you have the energy spacing h bar omega is equal to h bar the square root of k, the spring constant, over the mass. So now it becomes very clear that the larger the mass, the smaller the spacing. So for a huge mass, you will have an extremely small spacing here. And you can consider qualitatively that the k for the electron and for the nuclei is similar. comparable, and therefore, because of this huge mass difference, this spacing here is extremely small compared to the energy difference between the levels. We have seen before that this energy spacing is typically of the order of the EV or even larger in the course. So this is much smaller, and in practice, actually,
Excuse me.
yes.
So as you increase the n, the solution, the eigenvalues of for n is equal to 0 correspond to, okay, as you increase the levels, as you lower the levels.
This is the solution for at a given R
Yes.
for the electrons.
Yeah. Now, can't the solutions of given as like overlap each other as you go in the levels?
Well, the point is that we are interested in the lowest state at room temperature. And the point is that we will need just to focus on this, because this energy difference is actually very large with respect to what we are interested in.
Okay.
So basically, because of this very, very thin spacing, small spacing, it's enough just to focus on this part. This part will not matter because the energy difference is so large compared to what we are interested in. So basically, the consequence is that we can just focus on the n equals 0 case as electronic part and solve for that. So this is the consequence. So just to be quantitative, in practice, this delta E that is related to the vibrational mode is of the order of 10 to 100 millieV. So for the nucleus vibration, it's in the infrared. Corresponds to the infrared frequency, whereas the other difference that is between the electronic levels, delta En, is of the order of 1 to 10 eV, and this is in the visible or ultraviolet. Ultraviolet. So basically, we have a factor of at least 100 in the typical spectrum for these two types of modes. I mean, the electronic vibration and the electronic eigenvalues. So, because of this, well, I will, I guess I can, yeah. Well, okay. The consequence here is that one can just focus well, one can usually just focus and I'm talking about ambient condition on the n equal 0 case, that is electronic core state. Okay. Any question? Is it reasonably clear or the idea? You agree with the, okay. Starting from the equation we have for the vibration and having this type of potential for the electron, I'm telling you that the level spacing here is extremely small with respect to the energy difference between the electronic eigenvalues. And this can be seen by just considering that here we have a parabola and the eigenvalues, we know what they are, and mathematically one has something which scale like this, so if you have a huge mass, you are going to have an extremely small spacing. Of course, if one goes to something which becomes less parabolic, here one has a constant level spacing with something less parabolic. At higher eigenvalues, here it will, the spacing will become a little bit different, but one can qualitatively, for sure, for the lowest state, expect a spacing that is given like this. So, given the spacing is extremely small for the lowest state, which are the one one is interested in, one will have still a very, very large difference between the state here and the next group of states here that are associated with the first electronic excitation. So at room temperature, one can safely focus just on that part of the spectrum to get the property at room temperature. All right, so now another point I wanted to mention is that when the mass is of the order, I mean, for not the lightest maybe atoms, but for mass ratio that are of the order of 10 to the power 4, one can also use the classical approximation for the motion of the nuclei. So in addition, when the mass ratio is of the order of 10 to the power 4, one can treat the problem of the nuclei classically. That is when the mass is extremely large, the momentum is also very large, and one has the Heisenberg principle fulfilled, so one can, it's much larger than h bar, the uncertainty delta x and times delta p, and one can treat the particle classically. So in this case, the equation that was for the nuclei p square over 2 capital M plus E0 of R C of R this equation classically becomes 1/2 the mass of the nucleus times its velocity squared plus 0 of R is equal to the energy. So this is the simplification when one has not the lightest nuclei, let's say not hydrogen or lithium, helium, but something with a larger atomic number. Then one can treat the nucleus classically, and the equation becomes just the classical kinetic plus term plus the potential term is equal to the energy. And there, if you use this equation and you just derive with respect to time, you obtain 2 times mi times r second prime I times ri. So if I derive twice, I'm getting mi times the first derivative times the second derivative is equal, this is a constant, so minus dE0 of R with respect to Ri times Ri, the velocity. So in this case, one has this equation deriving with respect to time, and considering the velocity is not vanishing, the magnitude of the velocity is not vanishing, one can simplify. And this is the equation of motion that one obtains then for the movement of the nuclei. So it's just Newton's equation with, for the force, the derivative of the total energy that one gets from the electronic problem with respect to the position of the nucleus. And this gives us the equation of motion of the nuclei, the dynamic of the nuclei. So this is the way the properties of the nuclei can be obtained. Also the dynamics from the electronic problem. So the force that enters the equation for the dynamics of the ion is obtained as the derivative of the total energy E0, where this E0 is the solution of the electronic problem. That is the Hamiltonian for the electron that will be include its kinetic part, the electron-electron interaction, the electron-nucleus interaction, so this potential, and one also includes the nucleus interaction, which is just from the solution of the electron, just a parameterized term. That is, it's just for a given position of the nucleus, just a constant. So for a given position of the nucleus. So solving this equation for the electron, the Schrodinger equation from the electron, one obtains the eigenvalue, the ground state eigenvalue E0, and from this, for different position of the nuclei, one can then obtain the force acting on the nuclei, and therefore also obtain their equilibrium position, or have them with molecular dynamics move or vibrate at constant temperature, and so on. So this gives access to the structural properties of the system. So just in terms of terminology, when the non-adiabatic terms are vanishing or are neglected, let's say, non-adiabatic, so when the blue terms are neglected, one has the Born. This is what one calls the Born-Oppenheimer approximation. Physically, the rationale behind this approach, or the meaning, is that because the nuclei or the ions, depending if one is in a pseudo-potential approach or not, because of the nuclei or ion are so massive and therefore so slow with respect to the electron have the time to readjust and to be in the ground state when the ion moves. So the Born-Oppenheimer means that because the nuclei or ions are so massive, and therefore are so slow, with respect to the electron, that the electron at the time to readjust and be in their ground state. When the ion moves. When the ion moves. And slow, fast, you get it from what I showed you in terms of, showing you for the harmonic oscillator how the spacing scales with the masses. So this is the rationale behind the Born-Oppenheimer approximation. And now I just want to show you why in those cases the non-adiabatic terms can be neglected. So one can show it in a special case, but it gives an idea of what is the reason one can neglect these terms. So now, the non-adiabatic terms are small. When the electronic levels this is in general are well separated. And the mass ratio is very large. So now let's see why the non-adiabatic terms are small, considering a special case. That is, I consider simply an atom that is displaced. So the single atom that is displaced. So okay, so if I consider an atom with a potential like this, and that is placed at the position at the origin, and has, so this is the potential, and this is the wave function of my atom, C. So I consider my electronic wave function C and the position of the atom being at the origin. And then I move these atoms to a position R. And so the potential becomes this potential around the point R, and my electronic state immediately goes there, readjusts. So my phi will be here, where the potential of my atom is. So if I have a situation like this, where the electron immediately readjusts and is in its ground state around the potential of the nucleus. So I had initially my potential centered at the origin, and now I'm moving it to the position capital R. And I assume, well, this I should put maybe to be consistent with my notation for the electronic state, I was using the small c. So the wave function that was phi centered at the origin becomes the wave function phi centered around the vector r. So now the case where I can show rather easily that this non-adiabatic term is small is considering the second non-adiabatic term that had the second derivative, and I just focus on the diagonal matrix element. So, but okay, so I want to evaluate the second non-adiabatic term that I showed you in blue before. So I have to apply the second derivative with respect to the nucleus position on the wave function C of R minus capital R. So this I have to derive twice with respect to R. This C of R minus capital R. So when I derive this, I can also derive it with respect to the electronic position and change the sign. So it's equal to minus the derivative with respect to the small r of C of R minus capital R. And if I derive twice, then I recover the plus sign. So I'm getting the second derivative with respect to small r of C of R minus capital R. So this is when I rigidly move the electronic wave function, or if I assume the electronic state immediately readjusts to any displacement of the nucleus. So if I do that, then the second term, where I had to evaluate the matrix element of this R, the second derivative with respect to the nucleus position, and here I will just focus on a diagonal term. So we had something like h bar square over 2 times the mass of the nucleus, Cn of R, times this type of matrix element for the non-adiabatic term. And here I focus on the diagonal one. So I want to evaluate this. So this is equal to Cn R times, and here I'm going to write the ratio of the mass here, and then minus h bar square over 2m phi n gradient square phi n. And having seen this, I just replace this one by the gradient with respect to the electronic coordinate position. And this term here is just the kinetic term for the electron, that is the expectation value for the kinetic operator, which we know to be of the order of the eigen value for the electronic problem. So this T is of the order of the eigenenergy En of R. You know it for the hydrogen atoms, for instance. You have the real theorem. So this is of the order of the eigenenergy, and therefore, because of this ratio here, you have that this term is much, much smaller than Cn of R times En of R. So this is the rationale why this type of terms are so small. That is basically if the wave function moves rigidly, this is the type of expectation value of value one can expect from this matrix element involving this derivative on the wave function that essentially readjusts immediately to the displacement of the ion. So this is shows that these terms are very small indeed. I mean, I just showed it in one case. It's valid more generally. Okay? Any question? Okay, so I will stop here.